It was American web application company Basecamp that said, constraints drive innovation and force focus. Instead of trying to remove them, use them to your advantage. In this lesson, we're going to use linear programming. We're going to write an objective function. We're going to construct a feasible region given constraints. We will maximize an objective profit function, and we will minimize an objective expense function. All to answer the question, what is an optimal outcome? Before we get into it, let's take a look at warm-up number 2. Determine the vertices of the parallelogram formed by the lines y is equal to 2, y is equal to 8, y is equal to 2x, and y is equal to 2x minus 12. So the first thing that I did was drew this as a graph. This is going to give us the points 1, 2, 4, 8, 7, 2, and 10, 8. Now let's take a look at a problem you will be able to do by the end of this lesson. The To-Go Cup is a small business that makes two types of plug-in temperature-controlled beverage containers for home and auto use, To-Go Hot and To-Go Cold. As the name suggests, To-Go Hot will continuously warm the beverage to a set temperature, and To-Go Cold will keep a beverage at a continuously cool temperature setting. The cost for manufacturing is $25 each for To-Go Hot and $30 each for To-Go Cold. Nora and Anthony are the company owners, and they have found a local retailer who has agreed to promote and sell both To-Go Cup items in their store for a trial period of 2 months. The retailer will take an initial shipment of at most 500 items combined. The agreement is that at least 200 To-Go Hot and 150 To-Go Cold must be sold during the 2-month period. How much of each type must be made and sold to maximize cost? The optimal outcome in this situation is a minimum cost. Let X represent the number of To-Go Hot containers made and Y represent the number of To-Go Cold containers made. So the objective function is C is equal to 25X plus 30Y. The constraint is that X plus Y must be less than or equal to 500, and that X must be greater than 200 and Y must be greater than 150. Graph the inequalities, determine the coordinates of the feasible region, and identify the production amounts of each container type that will minimize the cost. Given the constraints, Nora and Anthony will have a minimum expense of $9,500 if they make and sell 200 To-Go Hot and 150 To-Go Cold containers. Sometimes the feasible region is not a closed polygon as seen in this graph. When this occurs, the feasible region is known as a boundless feasible region. In this whole unit, you've learned how to create, graph, and analyze equations that model a variety of financial situations. The techniques used are just some of the many ways to gain insight into the business decision-making process. In this lesson, you're going to learn a new approach, linear programming. This is a mathematical method in which the best outcome is the goal of the analysis. The best outcome of linear programming is known as optimal outcome. In business, an optimal outcome could be maximum profit or minimum expense. To achieve an optimal outcome, it is necessary to explore any limits to the resources your business requires. These limits are known as constraints. Here are a few examples of constraints: time for research, production, marketing, and sales; equipment that will be used in the manufacturing process; personnel for all aspects of production; raw materials that are available at the time of production; money to finance the project; demand by consumers for the product; supply of the product in a warehouse and in the marketplace; competitiveness to win over buyers in similar products. As the name linear programming suggests, the constraints used to model the situation will be in the form of linear inequalities. These constraints set up the boundaries for what can and cannot be part of the solution, just as fences are boundaries to areas that can and cannot be accessed. These inequalities may form what is known as a polygonal region. A polygonal region is formed by the intersection of a system of linear inequalities. Examine the closed polygon region and the lines that created it. The shaded rectangle is formed by the intersection of four linear equations. X is equal to 0, the y-axis, y is equal to 0, the x-axis, x is equal to 20, and y is equal to 15. The shaded region, including the sides of the rectangle, are formed by the intersection of the four inequalities, where x is greater than or equal to 0, y is greater than or equal to 0, y is less than or equal to 15, and x is less than or equal to 20. The next few examples are going to lead you through the linear programming process for a business venture situation. In linear programming, you look for optimal solutions. The optimization could take in the form of maximum profit or minimum expenses. Trax Corporation makes running shoes. It has two of the best-selling brands on the market, Elite and Bolt. The shoes are assembled at a warehouse by the machine and then finished by hand. It takes 0.3 hours for the machine assembly and 0.1 hours for handwork to make one pair of Elite. It takes 0.2 hours on a machine and 0.4 hours by hand to make one pair of Bolt. Since Trax makes other products at the manufacturing plant, they can allocate no more than 900 machine hours and no more than 600 handwork hours per day for the manufacture of Elite and Bolt running shoes combined. Construct a polygonal region to illustrate the situation. Let the X represent the number of pairs of Elite running shoes made and Y represent the number of pairs of Bolt running shoes made. There are four constraints that need to be modeled algebraically. Daily machine hours cannot exceed 900. Daily handwork cannot exceed 600. The Elite pair cannot be negative, and the Bolt pair cannot be negative. So the machine hours is 0.3x plus 0.2y is less than or equal to 900. The handwork hours is 0.1x plus 0.4y is less than or equal to 600. Elite pairs made is x is greater than or equal to 0, and Bolt pairs made is y is greater than or equal to 0. The graph of the system of inequalities on the same axis. The shaded area is the polygonal region. Notice that the equations form the boundaries of the region. The shaded region was determined by selecting all of the points that satisfy all four of the constraint inequalities. Let's check our understanding. Examine the polygonal region in that example. Identify whether each of the following points satisfies this system of inequalities. The 2000, 500, yes, that is within the shaded region. The 6000, 0, no, that's not. The 0, 2000, no, that is not within. And the 0, 1500, yes, that is. What type of polygon does the region form, and what are the coordinates of the vertices? Well, the polygon region is in the shape of a quadrilateral. A, the y-intercept of 0.1x plus 0.4y is equal to 600 means that x is 0, and so the y would be 600. So looking at this first equation, if x were 0, then we'd have 0.4y is equal to 600, which means y is 1500. So this point A is at 0, 1500. B is nice and easy being the origin of 0, 0. C is when 0.3x plus 0.2y is equal to 900, and at this point y is equal to 0, so x is equal to 3000. That means that this is at 3000, 0. To find D, we need to find the intersection of these two lines. So it's a system of equations, and we're going to use the elimination method for it. So we're going to multiply the top equation by -3, giving us a negative 0.3 minus 1.2y is equal to negative 1800. The second equation will remain the same. We will add both of these equations together to give us negative y is equal to negative 900. So y is equal to 900. Knowing that y is equal to 900, we can substitute that into either equation. Let's take 0.1x plus 0.4 times y, which is now 900, and let that be equal to 600. By solving this, we will find that x is equal to 2,400. That means point D is located at 2,400, 900. Examine this randomly determined polygon region in the first quadrant formed by 4 inequalities. Place a pencil flat on the page outside the polygon region, but not parallel to any of its sides. Keeping it parallel to the original position, slowly move the pencil over the region. What are the coordinates of the last point in the polygon region that the pencil passes over? Now move your pencil in a different location and orientation outside the region, but still not parallel to any of the sides. Pass it over the polygon and answer the same question. Repeat this 2 more times. In each of the instances, what you can say about the last point that the pencil passes over. Whatever the orientation of the pencil was in the start, the last point passed over should have been the vertex. The line represented by the pencil is called the objective function. In the context of finding a solution using linear programming, the polygonal region is known as the feasible region, since it represents the intersection of the constraints, inequalities, and contains all of the possible feasible solutions. In business, this linear objective function can represent profit or expense. Substituting values into the objective function that meet the constraints will yield profit or expense amounts. The maximum profit or the minimum expense will be determined by the objective function. This optimization will occur at one of the vertices of the feasible region. It is possible to note here that the feasible region is assumed to lie in the first quadrant, since in the real world the constraint variables will never be negative. For our work with linear programming, we'll include the inequalities x is greater than or equal to 0 and y is greater than or equal to 0 to remind you of this fact. The Trax Corporation from example 1 has determined that they make a profit of $20 on each pair of elite running shoes and $30 on each pair of bolt running shoes. Write an objective function that maximizes profit and determines how many of each type of running shoes should be made. As in the previous 2 examples, x represents the number of elite pairs and y represents the number of bolt pairs made. The profit objective function can be written as P is equal to 20x plus 30y. The vertex of the feasible region were determined in example 2. Evaluate the profit objective function at each of these points. Given the daily machine and handwork production constraints, the maximum profit that the Trax can expect is $75,000. To achieve this, they will need to produce and sell 2,400 elite and 900 bolt pairs per day. The To-Go Cup is a small business that makes 2 types of plug-in temperature-controlled beverage containers for home and auto use: To-Go Hot and To-Go Cold. As the name suggests, To-Go Hot will continuously warm the beverage to a set temperature, and To-Go Cold will keep a beverage at a continuously cool temperature setting. The cost for manufacturing is $25 each for To-Go Hot and $30 each for To-Go Cold. Nora and Anthony are the company owners, and they have found a local retailer who has agreed to promote and sell both To-Go Cup items in their store for a trial period of 2 months. The retailer will take an initial shipment of at most 500 items combined. The agreement is that at least 200 To-Go Hot and 150 To-Go Cold must be sold during the 2-month period. How much of each type must be made and sold to maximize cost? The optimal outcome in this situation is a minimum cost. Let X represent the number of To-Go Hot containers made and Y represent the number of To-Go Cold containers made. So the objective function is C is equal to 25X plus 30Y. The constraint is that X plus Y must be less than or equal to 500. and that X must be greater than 200 and Y must be greater than 150. Graph the inequalities, determine the coordinates of the feasible region, and identify the production amounts of each container type that will minimize the cost. Given the constraints, Nora and Anthony will have a minimum expense of $9,500 if they make and sell 200 to-go hot and 150 to-go cold containers. Sometimes the feasible region is not a closed polygon as seen in this graph. When this occurs, the feasible region is known as a boundless feasible region.